Welcome to AI Explains. Today we are looking at, well, the biggest star map ever created. It's called the Gaia Data Release 2. And if you're picturing a regular map, with cities and roads, that's not even close to the scale of this.
Oh, not even a little bit. We're talking about a census of our entire galaxy, the Milky Way.
A census, that's the perfect word for it.
It really is. I mean, the numbers are just staggering. We're talking about data on approximately 1.7 billion sources.
Mostly stars.
Mostly stars, yeah. It's like creating a detailed profile for every single person in a massive country.
Except the people are giant balls of burning gas.
And the country is 100,000 light years across. So, yeah, a little bigger.
And the key thing here, and I think this is what's so important, is that Gaia isn't just taking pretty pictures.
No, not at all. It's doing something called astrometry.
Which means it's measuring exactly where things are, how far away they are, and how fast they're moving.
Exactly. So for about 1.3 billion of those stars, Gaia gives us what's called 5-parameter astrometry.
Okay, that sounds terrifyingly complex. Let's break that down. Imagine you're explaining this to a 12-year-old.
Right. Good idea. So first, you have the position.
Where it is on the sky. Simple enough.
Simple enough. Then you have parallax.
Which is just a very, very clever way of calculating distance.
It is. And the last piece is proper motion.
How it travels across the sky over time.
That's it. So you combine those three things, and you know where a star is, how far away it is, and where it's headed.
So you're turning a flat map into a full 3D model.
A moving 3D model. But the profile gets even deeper than that.
Because Gaia sees in color, too. It has these blue and red photometers, right?
It does, yeah. A BP and an RP instrument. By comparing how much blue light versus red light a star gives off, scientists can figure out its surface temperature.
For about 161 million of them.
Yeah, it's really intuitive,
Yeah.
The color of the fire tells you how hot the fire is.
And then you have the real speed demons. For the brightest 7 million stars, Gaia also measures radial velocity.
And this is the missing piece of the movement puzzle. Proper motion is the side-to-side movement across the sky.
But radial velocity is?
It's whether that star is zooming directly toward us or speeding away. You add that in, and you can plot its true 3D path through the galaxy.
Okay, but to measure all this movement accurately, you need a background that isn't moving. You can't measure a car's speed if the road itself is shifting around.
That's a great analogy. You need anchors.
And Gaia uses quasars for that.
Correct. Over 500,000 of them. These are the super bright centers of incredibly distant galaxies.
So far away, they just don't appear to move at all from our perspective.
They're effectively stationary. They create what we call the Gaia celestial reference frame. It's the fixed background for the whole map.
Now, the map isn't totally perfect, is it? There were some visual quirks. I've seen the pictures. And there's that strange green patch near the galactic center.
Oh, yeah, the green patch. That's a fantastic example of a data artifact.
So it's not some weird green nebula.
Haha. No, it's just a spot where the stars are so crowded that Gaia struggled to get the blue and red color data we just talked about.
And software just...
The visualization software just defaults to green when that color info is missing. It's a glitch in the paint, not a cosmic mystery.
Okay, another thing that trips people up is negative parallax. That one sounds completely impossible. How can a star have a negative distance?
It sounds like a mistake, but it's actually just a statistical result. When Gaia measures really faint, really distant stars, it's pushing the absolute limits of its own precision.
So there's noise in the data.
A lot of noise. And sometimes that random noise just happens to make the measurement dip slightly below zero.
So you don't just delete those data points.
No, and that's the crucial part. If you just threw out all the negative results, you'd actually bias the whole data set. You have to keep the noisy data, both positive and negative, to understand the true statistical spread of what you're measuring way out there. It's still useful science.
Yeah. And the precision on the good stuff is just wild. I read that Gaia's resolution is so sharp it can see binary stars, 2 stars orbiting each other, that just look like a single blob to other telescopes.
It resolves pairs down to 0.4 arcseconds. That's comparable to the Hubble Space Telescope.
But for the entire sky.
For the entire sky, not just one tiny patch. It also tracked about 14,000 asteroids in our own solar system, sort of as a bonus.
But looking at the big picture, this is just an intermediate release, right? This isn't even the final map.
Not even close. This is all based on only 22 months of data. But even so, it has taken us from knowing the precise distance of a tiny, tiny bubble of stars right around the sun
to seeing the actual structure of the whole galaxy for the first time.
It fundamentally changes how we see our place in the universe. It really does. And, here's a thought to leave you with.
Okay.
If Gaia can track the motion of over 1 billion stars with this much precision, we can theoretically run the physics backward.
To see where our galaxy came from.
Or fast forward the tape to see how it will end.
That is a massive thought. Thanks for listening to this deep dive.